In this video, we're going to talk about the 7.1 notes, the first set of notes in topic 7, and this is going to be a discussion about related rates. So when we talk about related rates, the first thing we need to do is be able to recognize when we have one of these sorts of problems, so we're going to talk about that. But the main thing is going to be on focusing on the process for solving these sorts of related rates problems. So remember, basically everything we've talked about with respect to the derivative up until this point has been this idea of this rate of change, more specifically this instantaneous rate of change. So when we talk about the derivative, we talk about a way of expressing the instantaneous rate of change of a function at a certain point or at a certain value. And we can expand this beyond sort of just the graphs that we've been talking about, just the generic graphs that we've used to help introduce the derivative, to more practical applications or uses of this idea of rate of change. So something like, what is the velocity of a race car t seconds into a race? So at a certain point in time into the race, what is the velocity of the race car? What is the acceleration of a baseball t seconds after a pitcher throws it towards the catcher? Fix that in the notes. So again, this idea of instantaneous rate of change at a certain point in time. How much is a colony of bacteria growing t seconds after growth began? Again, instantaneous rate of change at a point. So in these sorts of cases, we're of course interested in this rate of change, but specifically with respect to time. In other words, when we're talking about rates of change, we might be dealing with additional rates of change to work with. So we talk about velocity with respect to time, growth with respect to time, but there might also be other things changing in the scenario as well. So for example, maybe you have two friends who are standing together, and then they each depart from one another. One walks due north, the other one walks due east, and you want to figure out how is the distance between the two friends changing at a certain point. So maybe after a certain number of seconds or a certain number of minutes after they've moved away from each other. Something like this. How fast is a radius of a spherical balloon changing at the point where the radius is 6 centimeters and the volume is increasing at a certain rate? Or how quickly is the level of water rising in a cylindrical pool when the radius is 2 meters, or with a radius of 2 meters and a length of 7 meters after a certain amount of time passes? So we still have this idea of what's going on with time, but now we might be dealing with scenarios where there's multiple things changing. There's multiple quantities that might depend on time, and we're interested in assessing the rate of change of one of those quantities. So there's a lot of stuff going on in typical related rates questions. There's more things in terms of the information. There's more variables to consider. There's more relationships to consider. And so what we're going to talk about in this set of notes is we're going to talk about how we can use calculus, of course, specifically derivatives, and our good old friend implicit differentiation to solve examples like these listed here. Now I'm going to highlight this just based on everybody's reaction to implicit differentiation every semester. This is a topic that a lot of people find difficult, which is understandable. It's not the easiest topic, implicit differentiation. But one nice thing about how we're going to be using implicit differentiation now compared to when we first introduced it is now when we do implicit differentiation, a lot of the times the equations that we're working with are easier than those when we introduced implicit differentiation. So if we go back, for example, to topic 5, just to emphasize this. In topic 5, we had equations like this, or equations like this, and we had to implicitly differentiate or find the derivative of y with respect to x. So a lot of these took a decent amount of work. What we're going to be seeing now is we're mostly going to be seeing equations that are like volume formulas or area formulas or the Pythagorean Theorem. And so the equations, rather than being something like this, will be something like x squared plus y squared equals c squared, or something like that, where it's a little bit easier to use the process of implicit differentiation. And the process itself, even though it's the same process, the equations are easier to work with. So I think a lot of people, again, just based on my experience, find implicit differentiation easier in this set of notes than when we first introduced it, because the equations we're going to be dealing with are a little bit easier than those that we used to first introduce implicit differentiation. So if this makes you nervous or makes you upset, hopefully it won't be as bad as it was when we first introduced it, because now, like a lot of the stuff that we will be doing with calculus, the processes get a little bit easier. We just need to have that nice solid base of knowing how to take derivatives and using derivatives. So that's why we spent all that time in the first 5 topics talking about techniques for differentiation. Now we're going to implement those techniques in things like this, where we're talking about related rates. So let's give a formal definition, or a somewhat formal definition, to what a related rates problem is. So when we talk about a related rates problems, these are problems for which you are given the rate of change of one quantity or maybe multiple quantities, and you need to use that information to find the rate of change, more specifically the instantaneous rate of change of another related quantity. Often, not always, but in most cases, related rates problems involve some sort of physical system where you've got 2 or more quantities depending on time. The quantities might depend on each other, not always, but frequently. And again, the idea is you need to determine this instantaneous rate of change based on some limited initial information. So the thing with related rates is they do sometimes initially seem daunting, because sometimes there's a lot of stuff thrown at you right away. So for example, if we take a look at this last example here, there's a bunch of values. There's this angle of elevation thing, which we probably haven't seen before. There's a lot of stuff going on. But like a lot of other things in math, and especially in calculus, I think these are easy to approach once we know what we need to solve for, which will just take some practice, and have a set of steps. So like we've seen with Newton's method, like we've seen with a couple other techniques that we've talked about, a series of steps is always, I think, a good way to start with some of these more complicated procedures, because then you know exactly what you need to write down, what you need to look for, all of that kind of stuff. So on the bottom of page 2, I have a set of steps here that should be helpful when dealing with related rates problems. And so, like always, rather than just talking through the steps, I'm going to go through these with our first example here on page 3. So we'll see how to implement these steps with this example, and then we've got 2 other examples that we can do to get a variety of different types of related rates questions, because there's a lot of different related rates types of questions out there. We're just going to be touching on some of them in this set of notes. In the additional practice problems, and of course in the dyno problems as well, there will be even more variety of types of problems. So if you want some more practice with this, this is another thing that is good to practice just to get used to how it works. There should be a good variety of questions for you to look at to help you with the web work assignment, to prep for the second midterm, all of that kind of stuff. All right, so let's take a look at this example. A spherical balloon is being pumped up with the helium being injected at a steady rate of 10 centimeters cubed per minute. And we want to figure out how fast the radius of the balloon is increasing when the radius is 5 centimeters. Okay, so a decent amount of information here. And again, it might seem a little bit daunting at first, but let's go through our series of steps and see exactly what we need to do, or what might help us figure out this sorts of problem. So the first step when we're dealing with related rates, I mentioned that a lot of these are physical problems, meaning that a lot of them lend themselves very nicely to being drawn. So if possible, even if you're not a visual person, I recommend this step because it helps kind of cement what we're doing in terms of the equations that we're going to need. First step is draw a picture if possible, and write down all the quantities that you know. So what are all the quantities that the question gives you, and see if you can relate them to each other in a picture if possible. So step 1, I'm going to draw a picture. So here we just have a spherical balloon being pumped up with helium. So I'm going to draw probably a really terrible balloon here. There's the opening. And it's being pumped up with helium, so I'm just going to indicate that we've got helium coming in here. And I have information about how fast the helium is being injected, and I have information about a certain radius size that I might want. So I'm going to need the radius of this balloon, so I'm going to just draw. It's a sphere, but I can draw the radius as a line here. I'm going to label that R. R is the radius. It's a good idea to label your variables so you know what they are, and for something like a midterm, if this is a written problem, we want to know what your variables are. So I've got the radius here. I might also want to talk about the volume, so I'm going to indicate volume with a V here. Where do I see volume? Well, if I look at this information, the helium is being injected at a steady rate of 10 centimeters cubed per minute. Well, this 10 centimeters cubed per minute, that's a change in volume. And so this quantity that I've underlined in blue, in red here, that's actually a rate of change for volume. And specifically, I can express that as the derivative of volume with respect to time. How much is the rate, or what is the rate of change of volume with respect to time? And I can see it's 10 centimeters cubed per minute. So I actually have a derivative, that rate of change of volume, with respect to time. So here, looks like that's all the information that I know, specifically about just the setup of this problem. The next thing I'm going to do here in step 2 is I'm going to note the quantity, which is usually a rate of change, that I want to solve for. So a lot of times with related rates problems, there's a lot of moving parts. So I think it's always a good idea to note the thing that we eventually want to calculate, just so that we know what our end goal is once we do all this stuff with the actual calculations and values. So my step 2, I'm going to write down what we want. So let's see. We want to figure out how fast is the radius of the balloon increasing when the radius is 5 centimeters. So what's my rate of change? Well, it looks like I'm talking about how fast the radius is increasing. So that sounds like a rate of change of the radius with respect to time. So for step 2, I'm going to say here that we want, I'm going to denote it as dr dt. The instantaneous rate of change of the radius. And I want this at a specific point. Specifically, I want this when the radius is 5 centimeters. So I'm also going to say here we want the instantaneous rate of change of the radius when the radius, which I've denoted r, is 5 centimeters. So in other words, I want this instantaneous rate of change at a specific point in time when the radius is 5 centimeters. Now, just a quick note here before we continue. I'm using one of the notations we talked about way back when we first introduced the derivative. Let me go back here to topic 4, when we were talking about the basic derivative rules here, 4.2. On page 2 of the 4.2 notes, I mentioned some different notations for the derivative. So up until this point, we've been using like f prime of x or like y prime if our function was called y. And that's typically because up until now, that's sort of been the easiest notation to write down, as far as just like writing down so much stuff. But the notation that I'm using now is more of this sort of style, Leibniz notation. Because, and this is going to help us with implicit differentiation here in a second, with Leibniz notation, it's explicitly stating what we are differentiating with respect to what variable. So when we talk about Leibniz notation, the d something on the top is the variable we are differentiating, or the function we are differentiating. And the variable on the bottom, usually an x, but here we see it as a t, that's the variable with respect to which we are differentiating. So if x is our variable, kind of like we've seen almost all up until this point, every time we see an x, we differentiate it as normal. When we did implicit differentiation, we were assuming that y was a function of x. And so technically what we were doing here with like y prime, this was the derivative of y with respect to x. And so every time we took the derivative of y, we had to remember it was a function of x, which meant we had to use that implicit differentiation's hidden chain rule and multiply it by y prime. It's going to be the same thing here, but now what I'm going to do is I'm mostly going to be using that Leibniz notation structure here because it helps us see, again, everything we're going to be differentiating is going to be with respect to time, to t. So notice for all of these derivatives, the variable of interest, the variable I'm differentiating with respect to, is t. And again, the reason I'm using this notation is because once we start actually expressing these quantities in terms of equations, the t is going to sort of disappear. And so this notation is going to help us remember that when we're taking the derivative of things, it's with respect to t, even if t isn't explicitly showing up in our equation. So that might sound like nonsense right now, but it's going to make sense in just a second in step 3 here, which is the step where we write down an equation that relates all of these quantities that we're interested in, both the known quantities and maybe the quantity that we're interested in solving. Maybe not always, but sometimes that shows up in there as well. So what's going on here? So again, usually these are physical examples where a lot of times the physical example comes down to a certain shape, like a sphere in this case, or a cone, or a pyramid, or a cylinder, or a box, or a triangle. And so a lot of times here in step 3, this equation is going to be some sort of relevant volume equation, or area equation, or even like the Pythagorean theorem when you're dealing with triangles. So if I think about what's going on here, I have information about a volume of a sphere, the radius of a sphere. I want some sort of instantaneous rate of change of the radius. So a good equation to relate all these things would be the volume of a sphere. And the volume of a sphere can be expressed as volume, V, equals 4/3 times pi times the radius cubed. So with volume equations, we'll talk more about this as the second midterm approaches. But with a lot of these physical equations, like the volume of a sphere or the volume of a cone, or like the area of a trapezoid, if that ever shows up anywhere, we'll provide you with the lesser known ones. So I think the only ones you'll need to worry about remembering are things like the area of a rectangle or a square and the Pythagorean theorem. Everything else, like the area of a circle, the volume of a sphere, volume of a cone, those we will provide to you either on the formula sheet, or if they're not on the formula sheet and they show up on the midterm, we'll let you know what that physical equation is. So if you're like, I don't know where this came from, or I haven't seen this in years, don't worry about having to go and remember that. We will provide you with everything beyond like the area of a rectangle or the volume of a box or the Pythagorean theorem. So just to hopefully lessen some worry about that. So volume of sphere, volume equals 4/3 times pi times r cubed. So this thing relates volume with the radius, which looks like the two main things we have here. We have information about the radius, information about the volume. So what we do here in step 4 is we look at that equation we had in step 3, and we implicitly differentiate it with respect to time. So before, when we were implicitly differentiating things like y, we were differentiating with respect to x. meaning that every time we were differentiating anything but x, so every time we were differentiating y, we had to multiply that by y prime, the derivative with respect to x. Here, it's the same sort of thing. I have two variables going on. I have volume and I have the radius. When I differentiate volume, when I differentiate the radius, I remember that these are both functions of time, just like y was a function of x when we were doing this with implicit differentiation, which means every time I take the derivative of v or the derivative of something involving r, I need to multiply it by the derivative with respect to time. I need to do that sort of hidden chain rule that we saw with implicit differentiation. Whenever we differentiated y, we had to multiply its derivative by y prime. It's the same thing here. It's just now instead of y, we have other stuff. And instead of x being the variable of interest, the variable of interest is t. So every time we're differentiating any other variable except for t, we have to multiply the derivative by the derivative with respect to time. So let's see what that looks like. I'm going to differentiate this implicitly with respect to time. So volume, v, that's just the variable, that's just the quantity. Derivative of the variable on its own, like the derivative of x, is just 1. But since volume is a function of time, and I'm implicitly differentiating with respect to time, I multiply that by the derivative of volume with respect to time. So this is just like what we were doing when we were taking the derivative of y and we multiplied it by y prime. It's just like that with implicit differentiation, except now it's volume instead of y. Okay, so there's my left-hand side. My right-hand side is this thing, which looks a little complicated, but remember 4/3 pi, that's just a constant. So I'm going to leave that alone, and I'm going to take the derivative of r cubed. R cubed, taking the derivative of that, I can use the power rule. That's going to be 3 times r squared. But remember, just like we did with v, it's a function of time, and I'm differentiating with respect to time. So since I took the derivative of r, I'm going to multiply it by the derivative of r with respect to time. That's that implicit differentiation. That's that hidden chain rule in implicit differentiation. So let's simplify this a little bit. 1 times the derivative of volume with respect to time is just dv dt. And then on my right-hand side, I have 4/3, and then I have this 3. The 3 on the denominator of 4/3 will cancel with the 3 next to that r squared. So my right-hand side can be written as 4 pi times r cubed times dr dt. So not as bad as some of those implicit differentiation equations that we saw back when we were first learning it. It's just every time we differentiate some variable that's not t, we multiply the derivative by that d something dt notation, indicating that it is implicitly differentiated. We're almost done. Step 5. Now I have this derivative, and I want to solve it for the unknown quantity. So this is like what we were doing with implicit differentiation, where we had some big derivative and we wanted to solve it for y prime. So we had it as y prime equals something. This is the same sort of thing. So in step 5, what I'm going to do is I'm going to work with this thing that we had in step 4, and I'm going to solve for the thing that I want, specifically that quantity that I wanted in step 2. This is the thing I'm trying to solve for in this equation. Now, in step 5, what I always recommend doing, which you usually can, is replace any sort of variable or quantity with the actual quantity it's supposed to be based on the problem. So we have dv dt, we have r squared. What's dv dt? Well, if I go back up here, I noted that the rate of change of the volume is 10 centimeters cubed per minute. So I can replace that dv dt with 10. Then I have 4 times pi. What about r squared? Or more specifically, what about r? Well, r is the radius, and the radius is changing because the volume is increasing. But if I look at step 2 here, the point at which I want dr dt is the point where the radius is 5 centimeters. So I can replace the radius in this equation with 5. So instead of r squared, I can write this as 5 squared. And then I've got that dr dt. So now I just have to solve this thing for the unknown. I just need to solve it for dr dt. So I want dr dt equals something. So let's see, I've got 10 equals, 5 squared is 25, 4 times 5 squared is 100. So I've got 10 equals 100 pi times dr dt. And if I divide both sides by 100 pi to isolate that dr dt, I get dr dt equals 10 over 100 pi, which is 1 over 10 pi. So this is the rate of change of the radius. What am I measuring things in? So volume is centimeters cubed because it's a volume. That's the units for volume here is the units cubed. The units are centimeters. When we think about the radius is just like a line, right? It's that distance from the center of the sphere to the edge. So it's just going to be measured in terms of centimeters as listed here. So that rate of change of the radius is going to be in terms of centimeters per minute. So in terms of units, we have this in terms of centimeters per minute. And so this is the thing we wanted. The instantaneous rate of change of the radius at the point where the radius is 5 centimeters. So that's this idea of related rates. We have some physical problem. We want to find some rate of change associated with that problem. So what we do is we consider a picture of the problem, and then by using that picture, it helps us figure out exactly what pieces need to go into this calculation, what pieces we need to work with in some sort of relating equation to help us solve for the unknown quantity, which again is usually some sort of rate of change. All right, let's do another one. Again, just to get some practice here with different shapes, different calculations, all this sort of stuff. So in this next example, we have sand falling from an overhead bin, which is accumulating in a conical pile with a radius that is always 3 times the pile's height. If the sand falls from the bin at a rate of 120 feet cubed per minute, how fast is the height of the sand pile changing when the pile is 10 feet high? So again, a lot of information is given in this problem in just a couple sentences. So the first thing we're going to do here to make this a little bit easier is we're going to see if we can draw a picture, just like we did above, and write down all the quantities that we are aware of. Okay, so let's see. Scroll back up here a little bit so we can see the problem. Sand is falling from an overhead bin, accumulating in a conical pile with a radius that is always 3 times the pile's height. So we have some sort of cone shape. Maybe something like this. So there's the cone of sand. Let's say we have some overhead bin here and the sand is falling down from there. And with this cone, we have 2 quantities. We have the radius, so the bottom of the cone is a sphere with a certain radius, and we have the height of the pile. So I'll say here r is radius of the pile, h is the height of the pile. Let's see, what else do we have? We're told that the radius is always 3 times the pile's height. So if I think about what the radius is here, I can actually come up with an equation for the radius. If the radius is 3 times the pile's height, I can actually say that the radius here, r, is 3 times h. So just expressing the radius in terms of height just by this information here. Okay, what else do we have? We have the sand falling from the bin at a rate of 120 feet cubed per minute. So that's the rate of change of the volume of the cone. So we also have a dv dt here, the rate of change of the volume, which is going to be 120 feet cubed per minute. So it's falling from the bin. We're assuming all of that sand is accumulating into the cone shape, so it can be thought of as the change of the volume with respect to time. So that looks like all the stuff we know. We've got a nice picture here. We've got some quantities. Let's see what we want. So in step 2, we write down what we want. How fast is the height of the sand pile changing when the pile is 10 feet high? So it looks like the quantity we're interested in here in terms of rate of change is the height. So what we want here is we want dH dt, the instantaneous rate of change of the height of the pile, and just like in the previous example, we want this at a certain point, that instantaneous rate of change at a point. Specifically, we want that dH dt when the pile is 10 feet high. So we want this instantaneous rate of change when h, the height, equals 10 feet. So this is the thing we want. So that was our step 2, the quantity that we want. And step 3, we want to write down an equation that relates all of these quantities. So here we had a sphere. We had information about the volume and the radius of the sphere. Here we have a cone. We have information about its height and its radius and some information about its volume. So for step 3 here, I'm going to write down the equation for the volume of a cone. Again, don't worry about having to remember this off the top of your head. It will either be given to you on the formula sheet or the exam or written answer, whatever it shows up as. If it shows up with a cone, it will be provided for you if you need this volume equation. So volume of a cone, volume V, can be expressed as 1/3 times pi times radius squared times height. So this is the quantity that we're interested in as far as wanting to get to the thing that we want. We want this dH dt eventually. Now, if we look at this, there's 3 different quantities, right? Volume, radius, height. Whenever we have a lot of variables, if possible, we want to reduce the number of variables to a more manageable amount. And actually, part of that was already done for us here. So we have volume, we have radius, we have height. But if we take a look at radius, notice that we already just expressed that in terms of what it means in relation to the height. So what I'm actually going to do here, before we differentiate this thing explicitly, is I'm going to rewrite this as volume equals 1/3 times pi. And for the radius, I'm going to replace that with what we said the radius was with relation to height. So instead of r squared, I'm going to replace the r with 3h. So I've got 3h squared times h. which is nice because now I have fewer variables to worry about. I just have v and h in here. And so one more time, I'm going to rewrite this as volume equals 1/3 times pi. Then I've got, let's see, 3 squared is 9 times h squared times h, which gives me, I'll just write this on the same line so we don't run out of room. 1/3 times 9 is 3. H squared times h is h cubed, so I can write this volume equation as 3 pi times h cubed for this specific case, because again, I'm told that I can express the radius in terms of the height as 3h. So this is the equation I'm going to work with here. Just a little bit easier than all of these variables in this expression. Okay, step 4. This is where we do the calculus part. This is where we implicitly differentiate the above equation with respect to time. So I'm going to differentiate what I've underlined here with respect to time. So derivative of v is 1. Since it is a function of time, I need to use that hidden chain rule with implicit differentiation, multiply that by dv dt. All right, so on the right-hand side, I have 3 pi. That's just a constant, so I'm going to leave it out front. And I'm going to multiply that by the derivative of h cubed. That's going to be 3h squared. And again, it's a function of time, so I need to multiply it by dh dt. So simplifying this a little bit, I have dv dt equals 3 times 3 is 9. 9 pi times h squared times dh dt. And again, this is the quantity I want to solve for. So now I have everything in terms of derivatives here where I've taken the derivative with respect to time. And so in step 5, what we do is we solve for the unknown quantity. So just like we did in the previous example, the first thing I'm going to do here in step 5 is I'm going to see if I can get rid of all those other variables, the dv dt and the h in this case. So dv dt, what's that? That is our rate of change of volume with respect to time. So that's 120. So I can replace that dv dt with 120. And then I have 9 pi times h squared. What's h? Well, h is a changing quantity. It's the height of this pile. But if I look at step 2, I want the instantaneous rate of the height when h is 10. So I can go ahead and plug 10 into my value for h here. So I have 120 equals 10 squared is 100 times 9 is going to give me 900 pi dh dt, which means I get dh dt, dividing both sides by 900 pi, as 120 divided by 900 pi. Now, of course, you can simplify this if you want to. I'm just going to write it. I should have done that up here too. I'll write this as well. Just approximately, like, what's the decimal value of this? 1 divided by 10 pi is approximately 0.03181 centimeters per minute, just to show you what it is in decimals, just because I think it's a little bit easier to see what the value is, the quantity is with decimals. We can leave this as it is if we want to. We can simplify it if we want to. Either way is fine. I could write this as, what is that, 2/15 pi. And this is a measure of the rate of change of the height. So the height is just a measure of how high the sand is above the ground. We're measuring things in terms of feet. So height is going to be in terms of feet. And so the rate of change is going to be feet per minute. So this quantity is in terms of feet per minute. And I'll give you the decimal approximation of that here as well. That's approximately 2 divided by 15 pi is about 0.042441 feet per minute. So that's how much, can't write minute for some reason, there we go. That's how much the pile is changing in height dimension per minute when the height is 10 feet. So same sort of an approach and idea as the first one here, just a different shape and a different rate of change that we were looking for. Let's do one more example here, and this one's going to be a little bit different. This is one where a picture is really going to help us, and this is going to be an example of a case where we could use some inverse trig function to help us get the final answer that we want. So in this example, a man has positioned a 3-meter tall ladder against a wall. He then begins to push the bottom of the ladder towards the wall at a rate of 0.01 meters per second. We want to figure out how fast the angle of elevation is changing when the bottom of the ladder is 1 meter away from the wall. So lots of stuff going on in this one. So let's start by seeing if we can draw a picture to get a better idea of what exactly is going on in this sort of an example. So we have a wall. Let's assume here that we're dealing with a wall that is at a 90-degree angle to the floor. Just an assumption here, but that's usually how walls work, so we can make that assumption. So there's my wall. I got my floor, and I've got a ladder. So let me just draw a little ladder here for us. All right, so there's the ladder. And what's going on is the ladder's bottom here is being pushed towards the wall at a rate of 0.1 meters per second. And we want to figure out how fast is the angle of elevation, the angle between the floor and the base of the ladder, changing at a certain point. So we're going to need some more things labeled here. This doesn't look like it's going to help us very much as it is. So, but it looks like the way that I've drawn this, it looks like I've got sort of a triangle shape going on. Specifically, if I consider the base of the ladder where it touches the floor here, where the top of the ladder touches the wall, I can think about this as giving me a triangle. Let's say this dimension is called x, the distance from the wall to the ladder's bottom. The distance from the floor to the ladder's top is y. And then the ladder itself is our third side of this triangle. And I'm just going to label that. That's not changing. It's always going to have a length of 3 meters. So I'm just going to label that as 3 meters. So let's see, what else can I label here? What's changing? The ladder's being pushed towards the wall down here. So I'm pushing on the ladder, which means that the ladder is moving closer to the wall along my x coordinate here, or my x side. I can actually express that as a rate of change. I can think about dx dt. So what's dx dt? Well, that I can think of as the rate of change of this side of my triangle. How much is that changing? I can see that the ladder is moving toward the wall at a rate of 0.1 meters per second. In other words, that's the rate of change of x. 0.01 meters per second. But I have to be a little bit careful here. Notice that because of the way that this x side is defined, as I'm pushing on the ladder, x is getting smaller. It's getting smaller by this amount. Because it's decreasing and not increasing, I'm actually going to denote this rate of change as being negative. So the rate of change of x, because x is getting smaller, is negative 0.01 meters per second. So it's important not to forget the negative there just because of the way this is constructed. X is getting smaller as that ladder's moving, so this rate of change is going to be negative. Now there's one last thing I want to write in here. We don't have a quantity for it yet, but I want to write in this angle of elevation. I want to show what this is in this drawing. So the angle of elevation is the angle between the floor and the base of the ladder. In other words, is this little angle here. I'm going to call that theta. So this looks like everything I know. Now let's see what we want. Step 2. How fast is the angle of elevation changing when the bottom of the ladder is 1 meter away from the wall? So the rate of change that we're interested in here is the rate of change of the angle of elevation. So what that translates to is we want d theta dt. The instantaneous rate of change of the angle, specifically when the ladder is 1 meter away from the wall, or in other words, specifically when that x side is equal to 1 meters. So this is the quantity we want, d theta dt, at the point where that side x is 1 meter long. All right, so step 3. So step 3 is where we relate these quantities with some sort of an equation. So sometimes when we have a construction like this where it looks like we're dealing with a triangle, sometimes the Pythagorean theorem is the way to go because that relates all those side lengths, right? A squared plus b squared equals c squared. Maybe c is like our 3 meters here, x and y are like our a and our b. But none of that really relates to our angle. And the angle, the theta, is really the thing we're interested in here in terms of its rate of change. So how do I relate something to theta? And what do I relate to theta? Well, there's a couple ways that we can work with theta here. There's a couple different things we could look at. The way that I'm going to look at theta is I'm going to try to relate theta to x, to this. And the reason I'm picking x is because, well, I've got the most information about x. I know its rate of change, and I know I need to use a specific value of x when I find the rate of change of theta. So I'm choosing x basically because I have the most information about x. So it might be easiest to relate theta to x in my calculations if I have a lot of information about x. So in step 3, I'm going to try to relate theta to x. Theta is an angle. X is a side length of this triangle. Now this is where it helps to go back to a little bit about what we talked about with trig functions. Everybody's other favorite topic. We've got implicit differentiation and trig functions going on here. Let me go back to topic 5 and inverse functions. So specifically with the inverse functions, I'm going to go back to this bottom of page 4 where we talked about the trig functions. So with the trig functions, we remembered that the trig function relates an angle to a ratio of side lengths. So we have some angle theta, and depending on the trig function we're using, we can relate theta to like the ratio of the opposite over the hypotenuse or the adjacent over the hypotenuse or various other relationships. So here, what's going on? We have theta here, that's our angle. X is like our adjacent side, right? X is the adjacent side like it is here with this example triangle. So maybe something that involves x. The hypotenuse here, our longest side, is the ladder. It's a constant. The ladder is not changing size. X and y are changing based on where the ladder is moving, but the ladder is always 3 meters. So it might be worthwhile to relate theta to x and to the hypotenuse, because the hypotenuse doesn't change, and we know a lot of information about x. So which of our trig functions relates an angle to the adjacent side and the hypotenuse side? Well, there's actually two. There's secant and cosine. Secant is just the inverse of cosine, so it's just 1 over cosine. So let's just pick cosine. Cosine's a nice, easy, relatively easy trig function to work with. And cosine of an angle is the ratio of the adjacent side over the hypotenuse. So if I consider what's going on here, if I think about cosine of theta, this is going to be the ratio of the adjacent side over the hypotenuse, which means that in this case, cosine of theta is going to be equal to my adjacent side is x, and my hypotenuse is 3. So a relatively easy relationship expressed between theta and x. Okay, now from this step, we can actually do a couple different, two different ways of approaching this. We could go ahead and use this in step 4, implicitly differentiate this thing with respect to time, or we could do something a little bit different. Now, it depends on your approach, it depends on your comfort level. Both things will get you the same result. But what I'm going to notice about this is I want d theta dt. Theta right now is buried in this cosine function. So when I think about d theta dt, I'm going to have to deal with cosine of theta somehow in that calculation. So actually what I'm going to do, and I will include in this set of notes the other way of doing this, so that you can see that there are actually two ways of dealing with this, is I'm going to rewrite this as an inverse trig expression. Now initially that's going to sound more complicated, but we're going to see that makes step 4 and 5, specifically step 5, a little bit easier. Now, inverse trig functions, bringing back yet another thing from our inverse function set of notes. Remember that our trig functions take an angle and give back a ratio of sides. So this is taking an angle and giving back a ratio of sides. An inverse trig function, so in this case, inverse cosine, is going to take a ratio of sides and give back an angle. So if x over 3 is our ratio of sides that we get from cosine of theta, inverse cosine of x over 3 should give us theta. So this is actually the function I'm going to use in step 4 when I do my implicit differentiation. And once we start that process, we're going to see why rewriting it like this may be a little bit easier than the other way of doing this, where we just take this initial thing, implicitly differentiate that, and then do the work. So we'll kind of see why I did this. This seems like an unnecessary, extra, maybe complicated step, but we're going to see its benefits here in just a second. Okay, so this thing is my equation from step 3. Step 4, this is where we implicitly differentiate this thing with respect to time. So let's see what we've got. I have an inverse trig function. I need to take its derivative. The inverse cosine function has a derivative of -1 over the square root of 1 minus x squared. Now notice here, my x is not just x, it's x over 3. I'm going to rewrite this as 1. Sorry, it's 1/3 x, just to make it a little bit easier to see. So I'm actually going to have to use the chain rule when I differentiate this inverse trig function. So the derivative of cosine of something, the derivative of inverse cosine of something is 1 over the square root of 1 minus the something cubed, the something squared. So that's the structure of the derivative of the inverse cosine function, this thing. But my something is not x, it's 1/3 x. So I'm going to leave that as my argument here. And by using the chain rule, I have to multiply this by the derivative of the inner function. The inner function is the 1/3 x. Derivative of 1/3 x is 1/3. Now, remembering what we're doing here, we are implicitly differentiating with respect to time. So I'm not quite done yet. I've used the chain rule. Now, I have to use the implicit differentiation chain rule, which tells me that I need to multiply this by the derivative of x with respect to t. Again, I'm differentiating with respect to time here. So every time I differentiate something, in this case something involving x, that's not a t, I have to take the derivative with respect to t. I have to do that implicit differentiation chain rule portion. So this side's a little rough. That's this whole thing. The derivative of the inverse cosine of 1/3 x is this. But the derivative of theta with respect to t, derivative of theta is 1. It's just a variable. Then using that implicit differentiation chain rule, I multiply that by d theta dt. And why is this nice? This is the thing I want to solve for. So I actually technically already have it solved. It's already isolated on this side. I just need to figure out what all this nonsense is over here. And then I have d theta dt. Okay, so here's my derivative. Let me simplify this just a little bit so it's easier for us to do step 5. So let's see. Oh, I forgot. I already messed up. Let me fix that here really quick. So I forgot the negative for the arc cosine derivative, so this should be negative 1. Sorry about that. Okay, let me simplify this a little bit. So I have 1/3. This 3 on the denominator here, I'm going to put on the denominator of this big square root term here. So I'm going to rewrite this as -1 over, again, I'm putting this 3 here on the denominator of that big fraction. 3 times the square root of 1 minus, now I'm going to square these terms. 1/3 squared is 1/9. X squared is just x squared. Multiplied by dx dt equals d theta dt. Okay, so this is now my equation here. I've taken the implicit derivative with respect to time. So now let me plug in what I know. So let's see. dx dt. What's dx dt? That was one of the values we were given up here. That was negative 0.01. So I can replace dx dt with negative 0.01. What about x? x, well, if I go back to step 2 here, I want d theta dt when x is equal to 1. So let's see what we've got. I'm going to replace those values. I have negative 1 over 3 times the cube root of 1 minus 1/9 times 1 squared. So replacing my value of x times derivative of x with respect to t. We said that was, whoops, I'm going too far. That was negative 0.01. Don't forget that negative. And this whole thing is going to equal to d theta dt. Okay, so let's see. How can I simplify this a little bit further? This negative and this negative are going to cancel each other out. That's going to give me, I'm going to put this 0.01 on my numerator, 0.01 over 3 times the square root of 1 minus, well, 1 squared is 1, so that's just going to end up being 1/9 equals d theta dt. And just to simplify that denominator a little bit more, 1 minus 1/9 is 8/9. So I can say here that d theta dt is equal to 0.01 over 3 times the square root of 8/9. This is the rate of change of an angle. All of the rates of change involving angles or anything involving angles that we're going to be dealing with in this course involve radians. So this is going to be the rate of change of theta, which is in terms of radians per second. So radians per second, everything here is being measured in terms of seconds. Theta is an angle, so we express its change in terms of radians. So this thing is the derivative that we wanted. And just to see what that is in terms of decimals, let me just calculate that here really quick. So this is approximately 0.0035336 radians per second. So that's how fast that angle of elevation is changing with respect to time. Now, a good thing to check, especially when you've got negative rates of change going on in your expression, is check the sign of your final answer to see if it makes sense. So here we have a positive derivative, a positive rate of change. Does that make sense? So if I think about what's going on here, as I push the ladder, the base of the ladder, the one next to the floor, towards the wall, what's going to happen is as this part goes towards the wall here, the top is going to start crawling up the wall. And so what's going to happen is as I push, let's draw a couple example ladders here, that angle is going to get a little bit bigger as I push the ladder closer to the wall. So that theta makes sense to have a positive rate of change because it is increasing. Theta is getting bigger, the angle's getting wider. So it makes sense for this to have a positive rate of change here, even though x had a negative rate of change. So it's always a good thing to check just to make sure the sign makes sense with your final answer. Now what I'll include in the completed notes is I'll show you another way of doing this, where instead of doing this rewrite, you just continue on with step 4 with this piece here. So you take the derivative of cosine of theta equals x over 3. You take the implicit derivative with respect to time. So you still have to do implicit differentiation. You still technically have to deal with inverse trig functions eventually. So even though it might initially look like you can avoid them by just using this in step 4 and step 5, you do need to use an inverse trig function to find the angle of theta to plug it into the derivative of cosine of theta. So some people find that easier, some people find this method easier. It really depends on your familiarity or comfort level with where you use the inverse trig functions, but they should both get you the same thing. So once these completed notes are posted, there'll be an extra page here at the bottom showing you the alternate way starting at step 3. But that's the idea behind related rates. You have some sort of physical problem, usually, where you've got a bunch of moving parts, a bunch of different rates of change, a bunch of different variables, and you're interested in finding a specific rate of change at a certain point. So the rate of change of the angle at x equals 1, or the rate of change of the height of the cone when the height is 10 feet, that sort of thing. So that's the idea of related rates.